Okay, okay, that's okay. It's okay, Professor.
Okay, okay. Welcome
Now,
everybody. Welcome
yeah.
everybody. My name is Yusuf Rashid. I am from Cairo University and I am the principal for the PL Pack software. Today, my talk about design of vibrating barriers using artificial neural networks in the conference Diacoma 24. I would like to thank my colleague Professor Paul Fu for giving me the chance to talk in this conference. As you can see, I'm talking about an application actually of the artificial neural networks for design what is calling vibrating barrier. So I will start by talking about what is the vibrating barrier. Then we will talk about method of designing vibrating barriers. Then we talk about the role of the artificial neural networks in designing of vibrating barriers. So actually, we are talking about application of neural networks is not development inside the neural networks itself. Vibrating barriers actually it is a device, a spring mass system device installed outside the building or outside the structure or outside the monuments. Actually, for example, you have buildings here, and this is the vibrating barriers here. The purpose of these vibrating barriers is to absorb the energy comes from earthquake. So instead of installing damper system or something inside the building inside or the monument inside or anything, we install something outside the building itself. So this idea of vibrating barriers are very good for monuments. For monuments or old historical building or something like that. And actually, this idea initiated by Professor Piero Cacchiola from Brighton University in England. And we had a project together between Cairo University and City University of London, Professor Ashraf Ayub, and Professor Piero Cacchiola is the founder of this method from Brighton University to study how to design this vibrating barrier for this monument. This is called the Zoser Pyramid. This is actually older than the Giza Pyramid, the well-known Giza Pyramid. It is outside. It's away from my home here in Giza by something like 40 to 50 kilometers. And actually, every weekend at morning, I go to drink a coffee over there in this nice place. So if this is a Cairo or Giza here in this area, so this is the place of the Zoser Pyramid. It is actually from, I think, the sixth dynasty or something like that. It's very old, very old. And we had huge earthquake by 1992 in Egypt. Actually, it was 12th of October. We celebrated its anniversary from 2 days ago. And actually, if you look at this earthquake, it is repeated every about 80 or 100 years. So I was about 22 years when this 22 years old when this earthquake strike Egypt actually, and it was awful. I had this experience. It was awful. It was about 5.9 Richter scale, but the problem it lasted for about 60 seconds. It was really awful, and this monument was deteriorated a lot from this earthquake. So we started to in this project between Brighton and City University of London and Cairo University in Egypt, between Professor Piero Cacchiola, the founder of this vibrating barrier idea, and Professor Ashfa Ayub and myself, Yusuf Rashid, to study how to design this. And we published this paper in scientific reports, I think by the 22 or some 23, I'm not sure about it. It was about how to design these vibrating barriers for seismic protection of those pyramid, and we used stochastic analysis. We use stochastic analysis mainly because we don't know the strength of the earthquake is going to strike. We don't know the intensity, the time series for this earthquake, how it will look like. So we need some probabilistic analysis in order to design something to stand with any earthquake to strike this monument. And the best thing, we are going to install this barrier outside the monument without touching the monument itself. And actually, we were able to design this vibrating barrier using this stochastic analysis. And we put two series from two directions like this. And another time we put four series around the pyramid itself. And we were able to minimize the peak acceleration at the top of the pyramid by about 27%. 27%. This was the maximum thing we were able to minimize this. And this is when we installed the vibrating barriers from two sides, and this is when we install the vibrating barrier from one side. If you look at the von Mises stresses for this shape, we reduce it a lot, really. It was about 27% reduction, actually. And actually, Professor Piero Cacchiola has done a very nice small model in the laboratory for the pyramid, and he put the vibe outside it, and he verified this result. Okay, the reduction mainly comes from the design of the vibrating barrier. For the mass we install it, the spring stiffness we install it, and the distance between the vibrating barrier and the pyramid itself. So these are the three factors we always look for. For example, if we change this barrier to be a bit away from the pyramid, we will have different type of reduction. So we are searching the optimum place actually to install these vibrating barriers, and we search the spring stiffness and the mass of the vibrating barrier we are going to install. And you can see the reduction. This is a black one without the vibrating barrier, and the red one with the vibrating barrier. You can see the reduction. It was about 27%. From where the neural network come now? And we decided this is very highly nonlinear problem and probabilistic problem, actually. Then we decide to design these vibrating barriers using artificial neural networks. And we published this paper at this year, 2024. And actually, it was design of the vibrating barrier for social pyramid using artificial neural network. The idea allowed us to reach a reduction about 46%. We were able to reach a reduction about 46% because of the use of the neural network. This is a pyramid. If you look at the pyramid, we have mainly 4 points. The point at the top, and then we choose another 4 points for the neural network training, and this is the VIBA. We put the vibrating barrier here outside the building by a distance d, and we have a spring system with stiffness k and mass of m mass. Before we start our generating the training data, we verified our model. Again is the experimental model and the finite element model. We used it in the stochastic analysis paper. And we were able, it is 3D finite element analysis, linear finite element analysis. We don't care about the nonlinearity of the soil because it improves the seismic energy absorption actually. So when we design using elastic analysis, that means this is the worst case we have. Okay, and we calibrated our model with viba, and without viba we obtained it from the stochastic analysis, and it was very, very nice. For example, the time period, it was 10.45 second, here 10.54 second. The peak acceleration, it was 13 something, here is 20.7. And the peak acceleration for the viba 9.6, here is 9.34. So we calibrated our model, the three-dimensional finite element model, and we started to use we use several types of artificial neural networks, especially recurrent neural network for earthquakes, but it doesn't give very good results. So the best result we obtained it using sequential neural network. So we have mainly two branches for input, one branch with 4 nodes and another branch with 10 nodes. These 4 nodes are the acceleration at these 4 points of the pyramid. If you remember these 4 points, I will come back to them here. These 4 points for the pyramid: point A, point B, point C, and point D. And which our choice here to put 4 nodes for the peak points of the maximum peak points of the training earthquakes. And then we choose some hidden layers, and our output layer, it was the 3 design variables we have is the stiffness for the viba, the stiffness of the mass of the viba, the mass of the viba, and the distance of the viba to the pyramid itself. Our training data, which our choice for the distance to the pyramid from 10 to 30 meters, and for the mass is 10 to 100% of the mass of the pyramid, and the stiffness covers a frequency range from 0.1 to 15 to lay the frequency of the pyramid itself. If you remember, it was about 10. It was 10 to cover this range. We generated about 6,300 training unit, and we use training data for 30%, 50%, 70%, and 80%, and 90%. And as you see, this is our neural network, the 2 input layers, 10 points and 4 points, and we have outside the output layer for the 3 main viba design points, and we use 50 and 100, 300 hidden layers, and we run our analysis with these nice learning curves, and we stop at when we have the loss, the minimum error we have, and we were able to, our target design to reach 38% reduction. Then we improved our, before this is the acceleration for the top of the pyramid. The peak acceleration for the top of the pyramid, you can see the reduction about 38%. We improved a bit our neural network to have optimized number of iterations. We put this one inside automatic optimizer, and we were able to minimize the error more in the learning curve, and we were able to reach 44% reduction. Okay, our training, we used 2 or 3 earthquakes, I can't remember, for training. One of them is the one generated from the response spectrum obtained from the Egyptian Code of Practice, and our testing mainly on the earthquake obtained, the rare record of the earthquake obtained at 1992, because it is repeated. So we expect we will see earthquake very similar to this one somehow. And we were able to now to improve the reduction to 44%. Then we decided and this is before the reduction, you can see the 44% here in the reduction. Then we decided to use the shaded analysis. This shaded analysis, it tells you which variable is more important in the design, whether it is the mass of the viba, or the spring stiffness, or the distance between the fiber and the pyramid itself. And we obtained that the string stiffness is the most influencing factor in the design. Okay, then we opened the area of the training data more to consider more training data for the spring, more frequency to generate spectrum, more spectrum in the training data. And we were able to reach the 46% reduction in the pyramid. And actually, we trained several other earthquakes. We reached within the 40 plus reduction in the peak acceleration of the top of the pyramid. You can see this is the rare reduction in the acceleration of the pyramid. Then we decided to use the same idea for other monuments. I have one guy is joining us the Zoom meeting now. He's working on this Sphinx because the Sphinx here is very weak at the neck area. So we were able to get the dimensions and the model of the Sphinx, and we are currently now designing this vibrating barrier for this Sphinx, and also we have done this for the Cairo Citadel, which is located at Cairo. This very old monument, but it's not very old. This is about from something like 300 or something like years ago, but it has two minarets like this. These two minarets, it changes things when we carry out a stochastic analysis. It's much better to use artificial neural network with this. You know, the artificial neural networks is not is easy, it's not a problem, but the problem is to generate these models using finite elements and calibrate it is not easy. And to use, we program the computer to generate training data actually, and we need huge computational facilities to run this problem. Before I end my talk, this is our place in Cairo University. This is our building, and this is our computational facilities. We have several workstations and all connected to great storage here, and with server we run our model on these machines. You can visit our website. This is our group, and we are very expert in computational mechanics, especially boundary element analysis, as some of you knew, and together with artificial intelligence. And actually we do artificial intelligence now in natural language processing in contracts for engineering construction. End up my talk. We used sequential neural network to design vibrating barriers, and we were able to reach 46% reduction, more than the stochastic analysis where we can reach something like 20% reduction. Actually, currently, we are trying the same neural network by optimization and to use multiple fiber. Instead of series of fiber, we use multiple fiber to use the mass we install inside it. And I think this Viba idea is very promising. We have to thank Professor Piero Pecchiola for this idea. And the idea of using neural network for the design is very also promising. These two together, we can design a lot of vibrating barriers for any monuments all over the world. I am very interested to join any of you if you are interested to design any Viba or anything. And our team is very ready and very expert in doing this stuff. Thank you very much for your talk. I ended my talk now. Any question, I will be pleased.
Thank you, Professor. Thank you for your impressive lecture. Any questions or comments?
Yes, I'm ready.
We can ask some questions.
Yes.
Okay, Professor, I have a question.
Yes.
Yeah, I noticed that you use the activation function. Did you try other types of functions?
No,
Are there
at the
some?
moment, no, but we are trying them now. actually.
Oh,
Actually, I will
okay.
tell you something. I will tell you something. Our main idea here is to use artificial neural networks in design Viber. Once we
Uh-huh.
have it, then we can improve. Then we can use different activation function, different types of neural networks, install optimizer inside these neural networks, and actually we can add something like physically informed stuff, because we have wave propagation in the soil actually. So we can add some constraint inside the neural network. We can add multiple fiber. We can add a lot of things. At the moment, we didn't try anything. Just we tried this one, and we get this idea. Then we publish it. Then currently I have about 4 guys are working in different areas to improve this model, because the best thing about this Viber is it is very very practical, and for monuments it's very difficult to ask them to do something to mitigate earthquake risk or something like that. So it's fantastic. You don't touch the monument itself, you install it outside it. Okay. In the same time you can install Viber for several buildings, for city, you can go outside the important city or something like that, install these Vibers outside. So currently we are investigating different parameters, different variables, especially when we have multiple Viber, how they are affecting each other. Okay. I hope some of you got
Okay, this
interested to
sounds
join us.
interesting.
Okay, if any of you are interested to join
Thanks
us,
for your
just
detail.
just let me say know on WeChat. I have WeChat or WhatsApp here. Just send me direct, and I
Oh,
will be pleased.
oh, okay, WeChat. Oh, yeah.
Yes,
That's cool, Professor.
yes,
Thanks for your detailed answer. So, is there any questions or comments?
yes.
Okay, thanks again for your impressive lecture.
Thank you.
So, maybe,
So
yeah,
shall I leave now?
thanks again.
Okay.